Okay, so this is the story of three temperature scales. So we're going to go ahead and talk about the three temperature scales. And we'll come back to the definition of temperature. There is the Fahrenheit, Celsius, and Kelvin temperature scales that we're going to talk about. So we're going to start off with first off the Fahrenheit scale, which is the one used here in the United States and mostly in the United States, not anywhere else. Although people understand Fahrenheit probably better than most of the other units that we have here in the United States. It was developed by a guy named Daniel Fahrenheit, a Dutch scientist, back in 1724, and this was the first one that was developed. And basically, the Fahrenheit scale was a scale that had a few of these temperatures defined. Okay, so the the 0 point was a mixture of salt and water. You mixed it a certain amount of salt with a certain amount of water, and this was the freezing point of that mixture of salt and water. As we're going to see, it freezes much lower than pure water itself. And the 100 degrees was set based on the assumption that normal body temperature is 96 degrees. So 100 degrees is a little bit higher than body temperature. Turns out that it's not 96, it's 98.6. But that's how he set it. And so that was Fahrenheit scale. Right? So he set the zero based on that. Let me go ahead and get a pointer out here. He set the zero based on that. He set the 100 based on that. Then he divided this segment here into 100 equal segments, and each one of them was a degree Fahrenheit. Then he kept the same size segments, went up, went down, and that's how we got the Fahrenheit temperature scale. Okay. Now, on the Fahrenheit temperature scale, um, two important points on there are the both the melting point and boiling point of water. Right. Turns out that water melts or freezes, because remember the freezing point and boiling point are the same. So uh, water both freezes and melts depending on which direction you're going, from solid to liquid or liquid to solid. Freezes at 32 degrees Fahrenheit. Okay, so 32 degrees Fahrenheit is freezing point on the Fahrenheit scale. If the temperature is below 32, you might expect there to be snow and ice as opposed to rain. And water boils at 212 degrees Fahrenheit. Okay, that's just kind of what it turns out to be. But those are kind of important points because, if you know what the temperature is, you can like expect there to be different states of water that are going to be prevalent at that temperature. So that's the Fahrenheit scale. The Celsius scale was developed by a guy named Anders Celsius. This one was in 1742. So this was like just 18 years later. Anders Celsius was a Swedish scientist, and he said, wait, we're always having to remember that the boiling point is 212 and the melting point is 32. You have to remember that. Um, why did Fahrenheit put zero here to be some random ice water mixture? And, you know, so what about water temperature? I think it's more important to know whether it's going to rain or snow in the forecast and whether water is going to boil or not. So he made a different temperature scale, which we call the Celsius scale, and he made the zero to be the melting point of water, right? Which is 32 on the Fahrenheit scale, so it's zero here. And the boiling point of water now he's set at 100. So just like Fahrenheit did, he said between this point right here, the 0 point on the Celsius scale, and the 100 point on the Fahrenheit scale, I'm going to divide this segment into 100 pieces, and each one of those pieces will be a degree Celsius. Now, notice that the difference between 0 and 100 here on the Celsius scale is bigger than the difference between 0 and 100 on the Fahrenheit scale, which means that each degree Celsius is bigger than each degree Fahrenheit. We're going to see that in our little formula that we're going to use to calculate between the two. Okay, so that's how he set the Celsius scale. Then he just took the same size degree and ran it up the scale, the thermometer, and ran it down, and he had his own temperature scale. So um, there's their two Fahrenheit Celsius scale. Now, how do you convert from one to the other? How if you know that today is 75 degrees and you call a friend who's in another country and you say, "Oh, it's 75 out today." And they go, "What? That's crazy. How can you stand it? You must be burning up." I'm like, "No, 75 is a beautiful day." And then they're like, "Oh, you must be using Fahrenheit. What is that on Celsius?" Well, if you want to go ahead and convert, you're going to use the formula. And here's how we develop the formula. Okay. First off, we got to understand that, let's see, uh, we kind of did a proportion calculation. Between 32 degrees and 212 degrees, there's 180 degrees, right? 212 minus 32 is 180. So that means that there's 180 Fahrenheit degrees between the melting point of water and boiling point of water. On the Celsius scale, there's 100 degrees between the melting point of water and the boiling point of water. Because on the Celsius scale, water melts at 0 and it boils at 100, right? Or ice melts and water freezes at 0. So to go between these two different points, it takes 180 degrees on the Fahrenheit scale and 100 degrees on the Celsius scale. So we said basically for every 180 degrees Fahrenheit, there's 100 degrees Celsius. But if you reduce that, 180 over 100, that reduces to 9 over 5. Divide 180 by 20, divide 100 by 20, you get 9 over 5. So you're going to end up with a formula that looks something like this. For every degree Fahrenheit to Celsius, it's going to be 9 over 5. Now you'll notice I have a minus 32 on here. The reason I have minus 32 is because we're not starting at the same place here, right? The melting point of water is 32 degrees. The melting point of water on the Celsius scale is 0 degrees. So here's on the Fahrenheit scale is 32. On Celsius, it's 0. So in order to make them start the same, what we're going to do is we're going to take the Fahrenheit scale and we're going to subtract 32 from it. So that's where this 32 comes in. So when we do our problems where we convert Fahrenheit to Celsius or Celsius to Fahrenheit, what you do is use this equation. Degrees Fahrenheit minus 32 over degrees Celsius is equal to 9 over 5. Remember that the 9 over 5 comes from this ratio, 180 over 100, just reduced to smallest terms to lowest terms, right? It's 180 over 100, divide both top and bottom by 20, you get 9 over 5. And the reason why we have the minus 32 is because this scale here is not starting at, the Fahrenheit scale is, the melting point's not at 32. So this is the equation that we'll use when we're doing conversions between Fahrenheit and Celsius. I think that's the harder conversion to make. We said there was 3 scales, and most scientists like to use the third scale, which we call the Kelvin scale. And this was developed by a guy named Lord Kelvin. I don't think that was his name. I think that, there was like a area or some place that was named Kelvin. And so this guy, I think his last name was Thompson actually, but he became a noble. He became a lord in Britain. And so they called him Lord Kelvin. And so now they use that name for the third temperature scale. So Lord Kelvin developed the Kelvin temperature scale. Now this was 1848, so this is over 100 years later. And the reason Kelvin developed his scale is because he said, "Hey, wait, there's a whole bunch of negatives here." Now, it's kind of nice to know that when a temperature is less than 0 or negative, it might snow. But we do much more than play with water in science. And actually, what they found is that there is actually some point where you can't get any colder than. And that point where you can't get any colder than is known as absolute zero. And so they were just had some research coming out with that point existing. Before that, they thought, well, you can just keep getting colder and colder and colder. But remember that temperature is a measurement of the amount of kinetic energy in a bunch of stuff. Most of the kinetic energy is just especially in a solid, is just vibrations or vibrating. So eventually, there's got to be a point where those vibrations stop, and that's absolute zero. So what they did is they found where absolute zero would be, which is actually 273 degrees below zero. And they said, "Oh, okay, well, let's why don't we make that so negative 273 degrees on Celsius is the coldest you can get. You can't get any colder. That's the point where all the molecules stop in a solid." So Kelvin said, "Well, why don't we just make that zero and then just move everything down?" So the Kelvin degrees are the same side as the Celsius degree. All they did was take the zero and bring it down 273 degrees, which means if you take the whole thing just straight down, then now your melting point of water is going to be 273. And since, once again, each Kelvin degree is the same size as a Celsius degree, then there's still 100 degrees between the melting point and boiling point. So it turns out the boiling point is 373. Okay, and so that's how they came up with the Kelvin scale. Well, that's how Lord Kelvin came up with the Kelvin scale. And it's a pretty easy conversion between Celsius and Kelvin. You just take the Celsius temperature and add 273 to it, and that gives you the Kelvin temperature. Right? So 100 plus 273 is 373. 0 plus 273 is 273. Negative 273 plus 273 is 0. All right. So whatever the Celsius temperature is, add 273, you get Kelvin, and vice versa. From the Kelvin temperature, you can subtract 273, it'll give you the Celsius temperature. By the way, if you're interested in what that turns out to be on Fahrenheit, it's minus 459 degrees Fahrenheit. Okay. Now, this next slide basically shows how they came up with this idea of absolute zero. What they did was they went ahead and they were doing. We're going to be talking about gas laws in second semester, and what they were doing is comparing the Celsius temperature of a gas with its volume. And what they noticed was, as the temperature increased, so did the volume. As the temperature decreased, so did the volume. They're what we call directly proportional. As one gets bigger, so does the other one. And as you can see, uh, a lot of these lines were created for different amounts of different gases. But all these lines all converged. And when you got down to zero volume, which you can't do, that's why there's this thing called extrapolation, right? They got data at higher temperatures with some volume in it, but they noticed the trend. And if you continue that trend, if you continue that line with the same slope all the way down, they all converged, and they converged at this point here, 273 degrees below zero on the Celsius scale. And that's what got people to start thinking, hey, what's going on here? As the temperature goes down, so does the volume until you get to the point where the volume is zero, which really can't happen. But if you follow the lines, theoretically, if you can get the volume down to zero, this would be the temperature at which that volume would be zero. And all of them converged at the same point because they would all be zero uh, at the same place. And so, and this was for volume. So the temperature was 273 degrees below 0 Celsius. They did some more experiments, and that's where they got this whole idea of a absolute zero. And then they went ahead and now found that negative 273 degrees Celsius to be that coldest temperature ever. It's actually negative 273.15 after a lot of research, but yeah, we'll accept negative 273 here. And then that's when they said, okay, that'll be zero on the Kelvin scale. Okay, so that concludes our story of three temperature scales. Here's the equation for Fahrenheit to Celsius. I will give you the equation. It's just whatever the temperature is Celsius at 273 to turn it into Kelvin, but I will give it in class. Okay, thank you for listening.